Hi everyone. Today we'll take a look at properties of geometric sequences and series. Okay, so before I begin, this video was quite a short video, not as long as the properties of arithmetic sequences and series, because unlike the previous video, I've only have one example question that I'm going to discuss here. Because the majority of the properties are, there are no direct questions that you'll get, but sometimes it's just important to know, and it's always useful to know the properties. So sometimes, if a question does come, it's not, it will strike to you. So you can always think of that. I'm not, you can be like, okay, this question is asking this, and how can I relate to it? Well, I know property number 4 of geometric sequence and series from this video. Okay, let's try use that and see if I can, manipulate and move around with the numbers and if I can reach anywhere, right? So essentially, I just, it's good to be aware of these properties. Again, if you're not, it's completely fine. There are a few properties which I will discuss, which you should know, right? Which is a must. And which are, even if you don't know them by heart, that's completely fine. As long as you know, if you see some examples, it should come to your mind, it should strike through. Otherwise, it's perfectly fine. All right, so let's get started with the first property. Okay, so the first property is, it will be the common ratio. The common ratio can be any real number. Okay, it can be any real number, but it cannot be zero. Right? It's just more of a conceptual thing, right? Like I doubt you'll ever find any questions regarding, oh, is it, anything, directly asking this, but this is just, just for you to be aware. Okay. So for example, if we have, a pattern, maybe like k, some constant, right? And if we have a common ratio of 0, then what's going to be the next number? We multiply by 0, right? So we get 0, and then again we multiply by 0, so we get 0 and 0, right? And this will go on, and it'll be 0, n number of times, as long as the sequence goes on. Now obviously, if you take a look at it, firsthand, you won't find anything wrong with it, right? I mean, what's possibly wrong? It's just being multiplied by 0, right? But if we use the definition of the common ratio, right? Common ratio is, suppose one is, if I say un plus 1 upon un, right? So the nth term plus the n plus 1th term, right? That's the definition of the common ratio. So if we use this definition, right? If we use this definition, right? So what's going to happen is, if we take the second term and upon the first term, so what do we get? 0 upon some constant number, right? Obviously, 0 upon some constant number is 0, so that's completely fine. But if we take a look at the third term over the second term, right? Because technically that should also give us the common ratio. So if we do that, what we get is 0 upon 0. Now, this is a problem, right? This is a problem, because we can have 0 in the numerator, that's okay, but we cannot have a 0 in the denominator, because any number divided by 0, technically, as any mathematics teacher would put it, gives us undefined, right? So the answer to this is actually undefined. There's no definite value, or some math teachers even say it's infinity, right? Undefined, infinity, they mean the same thing, because when there's a number to infinity, it's so large that you can't define it. Hence the word undefined, right? That's why we call it undefined. I think I've misspelled it here. I'll just rewrite it. So undefined, right? Okay, so this, because of this, we cannot have a common ratio of 0. Now, one more thing I would like to bring up here is an important thing, actually. So if we have a sequence, maybe like 0, or I'll just put in a different color before I begin, so it's easy to differentiate. So maybe I'll take it in orange. Okay, so if we have a term maybe like 0, 0, 0, and 0, and so on, right? Now, this can be considered a special case. How? Because, let me tell you why. If the first term is 0, anything multiplied, any real number you multiply with 0 will be 0. So in this case, the common ratio could be 1, 2, 3, pi, maybe the constant e, anything, right? It could be anything, because if as long as the first term is 0, if this is our first term, u1, and we multiply it with any of these constants, right? the next terms will be zero. So at this point, this is a geometric sequence, right? This is a geometric sequence. But if our u1 was, let's say, zero, let's keep it still zero, right? Because technically it is zero. But if our r goes zero, then it does not work, right? Then it's not a geometric sequence, not at all, right? So this is a different case, and in this, depending on what the common ratio is, really, that's what it all depends upon. If the common ratio is zero, obviously it's not a geometric sequence. But if the common ratio is any real number, it is a geometric sequence. All right, now let's look at the second property. So the second property is probably the most important property in this entire video. This property says that if A, B, C are in a geometric sequence, then B squared is equal to A into C. Now, if there's any one property which you should know out of all the properties that I mentioned today, it is this property. Okay, because you will find many questions with this property. Okay, and we did a question with using this property in a previous video, so you can check that out later if you want. I'll put that in the description if you guys want me to. That's fine. So how do we derive this, right? Let me talk about it very logically, right? So if we have A, B, and C in a geometric sequence, right? Geometric sequence. So what's happening is this is being multiplied by r. This is being multiplied by r every time, right? So on and so forth. So what we do is we write the common ratio. What is the common ratio? It's b upon a. Or if another way to write it, we can write it as r is equal to c upon b, right? This is also the common ratio because it's the next term upon the previous term, right? It's following the definition, nothing wrong. So now when we equate this common ratio and this common ratio, what do we get? We get b upon a is equal to c upon b. And if you simplify this a bit more, what do we get? B squared is equal to a times c, right? This is what we get. So this is the key thing, right? It tallies up with what I previously said before, right? This is the derivation. I mean, you can memorize this if you want, or you can use this logic. Initially, I always used to use this logic. I always used to use this logic and then work my way forward here because, sometimes, uh, when I started, I used to forget these, properties. So I just try to keep it as simple as possible in my brain. And I'm like, okay, let's work logically every time. It doesn't matter. I mean, I would spend like 10 seconds more doing this, but at least I'll never go wrong. Like I can work with that confidence. Okay, it's better to, know that you're not doing something wrong rather than do it fast and get it wrong. Right. So again, as if you do a lot of questions, you will memorize this. But initially, if you're not, just work with this logic, right? The common ratio is equal to b upon a. Then the common ratio is also equal to c upon b. When I equate it, I get b squared is equal to a times c, right? Okay, now let's look at a question with this. If pth, qth, and rth terms of a geometric sequence are themselves in a geometric sequence, then show that p, q, r are in an arithmetic sequence. Now, this is definitely an out-of-the-box question, and there is a little bit of manipulation, but you have to work along the same property which I previously told you, right? B squared is equal to A times C. All right. So what we can begin is we can say that if we're going to talk about the pth term, right? So if you talk about it in terms of general term, what is a general term essentially? It's un is equal to u1 times r, which is rn minus 1. So let's use that, okay? So if we get pth term, what are we gonna write? Up is equal to u1 times the common ratio p minus 1. Right, similarly for uq and ur, right? U1 is equal to r times q minus 1, and then rth term, right? So r is equal to u1 times common ratio r minus 1. Okay, so what's said that these three terms are in a geometric sequence also. Okay, don't get confused here. These are in a geometric sequence, right? There's a geometric sequence, and the pth, qth, and rth term are also in a geometric sequence. Okay, so if it might be confusing when you work with variables at times. So what I can do is I can give you guys a different example altogether. Suppose we have some numbers, right? A, B. Suppose we have these are in an arithmetic sequence, right? And suppose let's just say that this is the fourth term, the seventh term, and then the 15th term, right? I've just completely made this up. I don't even know if this will ever work, right? These numbers are in some geometric sequence, and this is the fourth term of the geometric sequence, the seventh term, and the 15th term. Okay, so what this question is telling us that this, this, and this, right? These terms are also in a geometric sequence, also, within themselves. So technically, these terms also create a new geometric sequence, right? This is the key to understanding this question, right? Oftentimes, that's what the wording can confuse you, right? And I know, I admit it's a little bit confusing, but that's what the question is supposed to. It's trying to confuse you. So again, let me restate what I previously said before, right? There are these terms in a geometric sequence, right? Let's take P is equal to 4, Q is equal to 7, R is equal to 15, right? They're not necessarily consecutive. We don't know, right? We can't work with the assumption that we know that, right? So that's telling us that these numbers are in some geometric sequence. Now, these numbers themselves, like the fourth term, the seventh term, and the 15th term, create a new geometric sequence, right? Maybe I don't even know. Like this could be anything for that matter. Like I honestly don't know. We could have maybe like 4, 16, 64. Maybe I don't know. Maybe there could be 8 in the middle. It could be some number in the middle. I don't know. I'm just like making things up just to make it clear for you guys. All right. I hope it's clear. So now let's move to the next part. So we know that this, and this are in a geometric sequence, right? We know that. So how can we move forward? Right, so let's use purple for that. Now, we know that these are in a geometric sequence. So what we can do is we can use a property, right? B squared is equal to A times C, right? Let's use this property. So this could be A, this can be B, and this is C, right? Because it's the middle term, right? It's in the middle. So that's why we take it as B. And the first term is A and the last term is C. Okay. So if we do that, what do we get? We get UQ, right, whole squared is equal to um, UP times UR, right? So UP times UR. Okay. So now I substitute for UQ. I'm going to substitute this in, right? So I'm going to get U1 times R raised to the power Q minus 1 whole squared. And I'm going to write here same thing, U1 times R raised to the power P minus 1. And here I'm going to get U1 times R raised to the power R minus 1. Okay, let's expand this a bit more. Okay, so if we expand this, what do we get? We get U1 squared times R raised to the power 2Q minus 2, right? What I did was I used the exponent's law, right? If an exponent is raised to an exponent, I can multiply. That's exactly what I did. Nothing special, right? Again, what I'm going to take is I'm going to put U1 and U1 and I'm going to multiply together. So I'm going to get U1 squared. And then if you can see, right, this is the same base, R and R, right? Exponents are different. So if something is being multiplied, we can add the exponents together. So if I add them together, what I get is R plus P, or I'm going to write P plus R, just the way it was before. I'll write P plus R minus 2, right? So now I can divide, if I divide both sides by U1 squared, they cancel out, right? So I'm going to cancel them. I'm left with what? R is equal to 2Q minus 2 is equal to R raised to the power P plus R minus 2. Okay. Now if I take a log with base R, right, what I'm left with, if I take the log, right, so I'm going to take a log base R raised to the power 2Q minus 2 is equal to log base R raised to the power P plus R minus 2. What happens is I'm gonna be left with 2Q minus 2 is equal to P plus R minus 2. If I add 2 to both sides, right, they cancel out. And I'm left with 2Q is equal to P plus R. And if you remember from the properties of arithmetic sequence, right, as you have B squared is equal to A times C, you have 2Q is equal to P plus R, or I would say 2B is equal to A plus C. So now that we have this pattern, this proves that we have an arithmetic sequence, right? That's it. That's our answer. So we have proved. Oftentimes you will find questions in the IB saying show that, right? And that's exactly what this question does. We're trying to show right? By the concept of the, or by using this property, simply we just use this property, and we were able to determine, or we were able to show that it's an arithmetic sequence. Right. Oftentimes, you might even have, to make the question tricky, they will say, simplify or determine what type of a sequence P, Q, R are in. Are they in a geometric? Are they in arithmetic sequence? And maybe if it's a paper three question, they might do something called a harmonic sequence, right? Again, paper three, something, questions can be out of syllabus, so they might explain what a harmonic sequence is, and they might ask you to show if it's in a harmonic sequence. Again, I'm not going to explain what a harmonic sequence is. If you want, you can Google it, if you're really curious. But I just told you just to tell you the different variations that can come, right? We might not necessarily tell us, the question might not necessarily tell us that, okay, this is show it, it's an arithmetic sequence, right? Because we knew that, we could work, keep that in mind, right? How do we show that some sequence is an arithmetic sequence? Well, we need to, we need to be able to show that it follows the property 2b is equal to a plus c. If we have that, we have an arithmetic sequence, period, and which we did. Right? And again, this was actually the use of two properties. The property here, this property, and the property 2b is equal to a plus c, right? This was the other property, right? So actually, you needed to know both of these properties in order to solve the question. Because I mean, you could have got at this point, and you'd be like, what does this mean, right? If you didn't know the property, you would have been stuck here, and that's it. Like, you wouldn't have been able to do anything else. Property number three: considering terms in a geometric sequence. I'm gonna write GS for short for me. Okay, so this is quite similar to the one that we had for an arithmetic sequence, right? If you remember, in arithmetic sequence, we had, when we're given that three random numbers are in an arithmetic sequence, we take, a plus d, a minus d, and we take that because the numbers can cancel out very nicely. So we're gonna follow, similar concept here, except obviously we won't have a plus d because there's no common difference. We're gonna have the common ratio. So what we do here is, if we have three numbers, right? Three numbers, what we take is, we take a, right? Or we can say some constant. I'll take constant just because it's easy to work with, right? K for constant, K. It's easier for me. Okay. So if we take K as the middle term, then we take KR and we take K by R, right? That's what we do. So for four numbers, right? If we're told that we have four unknown numbers, what we do is we take KR as one, we take kr cubed as the second or the last term, we could say. Then here we would have k by r, and here we would have k by r cubed. And note that the common ratio here is not actually r, it's actually r squared. So if you ever have a question, which has four unknown numbers and it's telling you to find the common ratio, if you just because you found the value of r doesn't mean you found the common ratio. Common ratio here is actually r squared. This is very, very important. Okay. Now, right, and here the common ratios obviously are. So I'll just mention it here. Common ratio is r. Okay. And I don't think you need five numbers ever, because that would just make the question lengthy. And at that point, IEP is not really testing your conceptual knowledge. They're actually just testing your speed at that point. So I don't think five numbers will ever be the problem. If five numbers ever do come, you can just use this and extend this entire again, right? You would have k by r squared and kr squared as the next previous term and the next term. Okay, that is the third property, and this is also, in my opinion, a very important property, right? There's a good chance that you might find questions with this property as well. So property number two and property number three are probably the most important properties in today's video. All right, the fourth property. If each term of a geometric sequence is multiplied or divided or raised to the power by the same non-zero number, then the resulting sequence is also a geometric sequence. All right, let's use an example. Okay, so the example I'm going to write here is the sequence that we're going to use is 2, 4, 8, 16, and so on, right? That's a very simple sequence multiplied by 2 every, the common ratio is being multiplied by 2 every time, right? Okay, so what this says is, if you have a sequence and you multiply, divide, or you put an exponent, right? Same constant value every time, you get a geometric sequence as well. So now if I divide this by 2, right? Let's work very simple. If I divide this by 2, what am I left with? 1, 2, 4, 8. right? This is also a geometric sequence, right? And the common ratio is still 2, right? Now, note that in this case, the common ratio is 2, but it doesn't mean the common ratio will always be 2, right? Just remember that, right? It might even be 3, it might be 4, but it will remain a geometric sequence. That's the key to remember, right? This is the key, right? Okay, so now if we multiply this by 2, what we did was we divide by 2 here. Now let's multiply it by 2. I'll just put a line here. And if you multiply by 2, well, what do we get? We get 4, 8, 16, 32. Okay? If you note here, the common ratio is still 2, right? Everything's being multiplied by 2. Right? That's okay. That doesn't matter. It can be 4, it can be 3, it can be 10, it could even be pi, right? It doesn't matter. But it's still in a geometric sequence, so it's good. Now, if we put some exponent, so if let's see, let's take the most simplest case here. Let's put an exponent of 2. So if we square this, if we square all the terms in the geometric sequence, what do we get? We get 4, we get 16, we get 64, and we get 256. Okay, so now the common ratio has changed. It's actually 4, right? 4 times 4 is 16, 16 times 4 is 64, 64 times 4 is 256. But it's still in a geometric sequence, and that's what matters. So this is, I've just showed you, we divided here, we did division, we did multiplication, and we did exponent, right? So I'll just write e to the power x, something like that. So we did all that, and you can still see it's in a geometric sequence. Now, where can this possibly, come handy? Say you have some geometric sequence in terms of variables, right? Not in numbers, in variables. And you're asked to, maybe to show that, or maybe you're asked to, show that something in terms of something, right? And you must have seen a previous question. We did something, show that these two terms in terms of a and b, if you remember, and there was something to this power so is equal to square root of ab, right? Something like that. So maybe you're trying to manipulate some numbers, trying to adjust it and meet its criteria, right? Meet the situation's criteria. So that's when this property can come useful. Maybe if you multiply by 2 or you divide by some constant number 2, make the sequence a lot more simpler, right? Because it's still in a geometric sequence. You can use this. You can use this idea. You can use this concept. Okay. So now if I'm going to put this in general terms, I can do that as well. So let's change the color. I'll take yellow. Okay. So maybe if we have some k, kr squared, dot, dot, dot. Okay. So maybe I'll just do something like a by b raised to the power k raised to the power m. And same thing here. So a b kr raised to the power m, a b kr raised to the power m, right? Geometric sequence and geometric sequence, right? That's all good. Right? This was property number 4. Okay, so this is the fifth and the last property of today. So the fifth property is not exactly, I won't, do it the same way I've done it for previous properties. I won't list anything out. I'm gonna, give you a situation here. So if we have two geometric sequences, right? So I'm gonna write GS1, geometric sequence 1, where we have A1, B1, C1, right? And here the common ratio is R1. Okay, that's what I'm saying. And we have geometric sequence 2, where we have A2, B2, C2, right? Dot, 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 goes on. And here the common ratio is R2. So if we multiply GS1, or geometric sequence 1, with geometric sequence 2, what we get is A1, A2, B1, B2, and C1, C2, right? And so on. And the common ratio, I'm going to write R dash, like this is the new common ratio. So, right? So the R dash, or the new common ratio, will be, it'll be R1, R2, right? Basically means R1 multiplied by R2. So now let's show this with an example, okay? So if I have GS1, right? If I have GS1 as 2, 4, 8, right? Where the common ratio is 2. And if I have my second geometric sequence, which is 3, 6, 18, right? Every time it's being multiplied by 3. So here I'll have common ratio is 3. Oh, sorry. I'm very sorry. I kind of messed up here. So if I keep the common ratio as 3, right? I was thinking in terms of arithmetic sequence. So if I keep the common ratio as 3, I get 3 times 3 is 9, and 8 times 9 is 27. Okay? So this is my common ratio. Now if I multiply these two, what am I left with? I'm left with 6, 36, and 28, 27 times 8, right? So 27 times 8, 56. 8 times 2 is 16. 16 plus 5 is 21. So I'm left with 216, right? And now here, common ratio will be 3 times 2 according to this property, which is 6. So as you can see, this is multiplied by 6 and it gives me 36. When I multiply 36 into 6, I get 216. I can even show that to you right now. So if I do 336, I'm gonna do this pretty smartly. I won't do it the normal way that we do it here. So if I do 6 times 30 plus 6, right? So I'm left with 180 plus 36. 180 plus 36 is 216, which matches right here, right? So this is the new sequence that we have, and it matches the property what we told, right? If we multiply two sequences, we have to, the new common ratio is R1 times R2, okay? So again, this is not, you won't find any direct property where, you won't find the direct use of this property where you're given two sequences and be like, oh, tell us the new common ratio. No, you won't. You'll probably be given, two sequences, maybe in terms of the variables. Maybe something like A1, A2, A3, or something like that. And then they might put in some catch, okay, this is, not exactly the, maybe there's in some other term with some other variables, right? I'm just making things up with the different scenarios here. And, you are trying to find the new common ratio in terms of the previous not variables. Something like that, something what we had for property number 4, right? So you can expect some question like that. The very low chance. Again, majority of the questions in IB will be revolving around property number 2, right, and property number 3, right? These are the main properties in the IB that you want to remember. The rest are just for, just be aware of them. Just know that they exist, right? Don't be like, oh, does that even exist? No, you just want to be aware, right? Even if you forget it once in a while, it should like strike when you see a question that's trying to explain something like this. Other than that, it's completely fine. Like I said, this video is going to be a pretty short one, and because I didn't do many example questions like I did for arithmetic sequences. And yeah, that's about it. So this video wraps up the entire sequences and series portion for the IB mathematics for SL and HL, right? And next chapter that we'll take a look at is proofs. So I'll put an introductory video on that, just giving you guys a brief on the different proofs that we have, and then I'll make a separate video for each proof. Again, proofs is again a very logical chapter. Not much conceptual knowledge you need to have, right? I'll get more into it when I put that video, when I explain that. So till then, you guys can revise. If you have any questions, put in the comment sections. Let me know. I'll be more than happy to help you out. All right, so that was all for sequences and series and for this video, and I'll see you in the next one. Bye bye.